Hello, welcome to Electronics Education. This is Vincent Chang. In this lecture, we are going to continue our learning around p-n junction in thermal equilibrium. P-n junction in thermal equilibrium, part 3, built-in potential. Built-in potential. Let's start with what we learned before around the fundamental semiconductor physics. There's a topic called carrier drift and carrier diffusion. And then taking these two forces together give us the net current density. So on the left-hand side is the net electron current density. On the right is the net hole current density. So both equations, the first term of both equations represent what? The forces coming from the electric field. So it's the drift component. And the second term, the second component from those two equations are from the concentration gradient. So that's component associated with the diffusion component. So the drift component plus the diffusion component, so give us the total, the picture, the net current density. And on the left is for electron. On the right is for hole. So you got to pay attention to, there's a positive sign for the electron expression, but there's a negative sign for hole expression. So now we're going to apply this. Try to know how to solve the built-in potential we learned from the previous two lectures. Net current density in thermal equilibrium. Net current density in thermal equilibrium. We know in the thermal equilibrium of the p-n junction, the net current is zero. The net current is zero. That means what? That means two forces are balanced out. The diffusion component will be canceled out by the drift component. The drift, again, coming from the electric field. The diffusion coming from the cause of the diffusion is concentration differences or concentration gradient. So when net current is zero, then we can find out the relationship. We can find out the electric field. We can solve the electric field. And let's take what we learned before. There's a relation called Einstein Relation, describing the relationship between the fundamental two parameters. One is called diffusivity. The other one is called mobility. The ratio of diffusivity and mobility, diffusivity in the numerator and the mobility in the denominator, is a constant. But the constant depends on, it's the temperature-related constant. I should say this. Boltzmann constant, T times T, absolute temperature, divided by electronic charge. It's called thermal voltage. It's called thermal voltage, all right? So if we take the ratio of dP over mu p goes to the thermal voltage, then we get this. VT over P dP dx. And then this is the equation for the built-in electric field. And then if you cancel out the dx from the both sides, you get the dV in terms of dP. dV means the differential for potential. The dP means the differential for concentration. For the whole carrier, what is the dV? We know this is the electrostatic potential distribution. Electrostatic potential distribution along the dial. So the dV is any differential segment of the potential curve. Any differential segment along the potential curve any segment, okay, any segment, differential segment along. So I'm trying to give you a hint of what? You need the integration. So sum of the infinite segment from the left to the right give us what? Give us the total difference. Integration. From the left end, left boundary, negative xp to the right boundary, xp. Give us the built-in potential. The built-in potential. And then if you ever learn the calculus, then you know how to solve this. Natural log. It's a natural log, right? So it's a natural log and then subtract from the upper bound to the lower bound. So Vt, natural log. And subtract means the ratio in the log scale. So let me just follow me, okay? Negative Vt and then what? Natural log P, the up boundary is the P of xn divided by P of negative xp. And then if you flipped, then you absorb the negative, all right? The basic property for the log. And then what? Then the negative xp, is the left bound. Xn is the right bound. So left bound, the whole carrier concentration on the left boundary equals what? The majority carrier concentration of the p-type semiconductor, PPO. And the right bound is the minority, the PNO. So PPO over PNO. And the PPO, if the acceptor atom concentration for the p-type is Na, assuming the donor atom concentration for the n-type is Nd, then you can solve the PPO is Na. NPO is Ni squared over Na. And NNO is Nd. And PNO is Ni squared over Nd. Am I going too fast? The O means what? The second subscript. The O means the thermal equilibrium condition. And the first subscript means the type. So on the left hand side, so it's the first subscript is the P. The P means the P type. In the thermal equilibrium, the P type semiconductor is what? The big P, whole carrier concentration. The second, in thermal equilibrium, the P type semiconductor, the big N, the minority electron carrier concentration. NNO and the NPO represent what? Electron carrier concentration in the N-type, majority. Whole carrier concentration in the N-type, minority. All right? So then you can get this. PPO is replaced by Na, and the PNO replaced by Ni squared over Nd. So here's the outcome. Something that you need to be very familiar. How to solve a built-in potential of the PN junction. So based on four things, right? Thermal voltage, impurity atom concentration, acceptor and donor concentration, and intrinsic carrier concentration. So basically it depends on material, because material decides the intrinsic carrier concentration. Temperature and the dopant concentration, the impurity, dopant concentration. Here's the takeaway. Assuming the p-type is the dopant for the p-type is Na, n-type is Nd. And then you have the built-in electric field, potential, electrostatic potential difference, distribution, potential difference, and then here's something that you need to be very familiar. Sometimes you need to remember this. All right? Thermal voltage, natural log, the product of the impurity, dopant concentration divided by intrinsic carrier concentration, Ni squared. So this is the end of the lecture. I hope you enjoy and learn something from the fundamental semiconductor physics of for the p-n junction. Thanks for watching.